Our first report will be made by Dr. Hai-Tao Shu about transport and spectral properties of heavy quarks from lattice QCD. Could you please show your screen, your lectures?
Yes, thank you.
Thank you.
Can you see my screen now?
Yes.
Great.
You have 25 minutes.
Okay. Hello, everyone. I'm Hai-Tao Shu from Bielefeld University. So today I'm going to talk about the transport and the spectral properties of heavy quarks from lattice QCD. My talk consists of two parts. The first part is the spectral properties of heavy quarks, and the second part is the transport properties of heavy quarks. And they are based on our 2-hour works shown here. So as you know, QGP is believed to be produced right after the heavy collisions. And after that, it will soon expand and then cool down. And what people really could see is a bunch of particles in the end. And quarkonium, which can only be created at the early stage of the collisions due to its large mass, can be used as a probe to examine the existence of QGP. This is because some of the quarkonium could survive throughout the whole collisions, where some of them will dissociate in the hot medium due to thermal effects. That's why it's also called a thermometer of QGP. But there are two questions remain unclear here. So first is the dissociation temperatures of quarkonium, which originates from the observation in the experiments that a sequential suppression in the production of quarkonium can be seen. And the other question is the transport properties of heavy quarks released from this heavy quarkonium. And it's usually characterized by a quantity called heavy-quark diffusion coefficient. This is an important input for the phenomenal and the transport models to explain the experimental data. You could see here that different choices for this parameter in different models don't agree well with each other, and they also deviate from the experiments a bit. Actually, these two questions share one same solution. That is the hadron spectral function, which carries all the information that we want about the medium properties of quarkonium. Here is a sketch of the hadron spectral function at the different temperatures. As you see, at very low temperature, there are only several very sharp bound states. And if you increase the temperature, you will see that these delta lag bound states will broaden. And also you can see a sharp transport peak appear at the small frequency part. And the slope of this transport peak is related to the heavy-quark diffusion coefficient. And if you keep increasing the temperature to infinite, for instance, you will see that all the bound states are gone and only the free continuum will be left. So you know that we could directly read off the dissociated temperature from the deformation of the spectral function, and also the heavy-quark diffusion coefficient from the shape of the transport peak. Even though the hadron spectral function is very important, but actually we cannot calculate it directly from lattice QCD. And what we could calculate instead is the Euclidean current correlation functions. It's related to this spectral function via a Laplace transformation after performing analytic continuation. Actually, extraction of the spectral function from the correlation functions is an EU-post problem, as the number of data points in the correlators is usually of order 10, but the spectral function is a continuous quantity. And to solve this EU-post problem, there are a number of methods in the market. And in this work, we will use a cascade fitting with theoretically inspired ansatz. Now we are ready to measure the correlators on the lattice. So this is the lattice setup that we used. So you see we have 4 different large fine isotropic lattices in the quenched approximation. And in each case, we have 5 different temperatures and 6 kappa values, which are responsible for the quark mass. And in our calculations, we use a Clover improved Wilson fermions as the valence quarks. So as I mentioned, we have a wide range for the kappa value. So how can we get the correlators at correct hadron mass? For that, we could extract the squaring mass from the correlators at a different kappa at below TC temperature. At this temperature, the squaring mass is believed to be the same as the pole mass, so we just use the squaring mass. Here, these discrete colorful points are the extracted squaring mass. You could see that they cover the physical upsilon mass and the physical gypsum mass, but none of them are exactly sitting on the physical line. So we need to interpolate the correlators to the physical line. So how do we do that? We first put all the correlators at a different distance and squaring masses here in this figure, and we feed it with ansatz of this type. And we could see that these ansatz could describe our data very well. So now we just insert the physical meson mass to here, and then we get the correlators at the physical mass. So here is an example of the interpolated correlators to the charmonia mass. As you see here, these black data points are the interpolated correlators at the different distances. Now we repeat this procedure for different lattices and the temperatures, and we get the, for instance, the correlators at the physical charmonia mass at 1.5 TC on different lattices. Here you could see clear lattice cutoff effects. So we need to perform a continuum extrapolation to reach the continuum limit. And we found that an ansatz of this type could give us a well-controlled continuum extrapolation. Now we show the temperature dependence of the correlators. So the left-hand side shows the charmonia correlators at different temperatures, while the right-hand side shows the bottomonia correlators. We could see that charmonium will change more as temperature changes, which means charmonia is suffering from more thermal effects. But to have a detailed study for these thermal effects, we have to look at the spectral function. Basically, the spectral function consists of 2 parts. The first is the UV part, namely the large frequency part, and the second part is the error part, namely the small frequency part. So for the UV part, there is already a perturbative calculations for the spectral function, which denoted as rho v pert here. And to accommodate it on the lattice, we need to introduce 2 parameters, A and B, to account for the uncertainties. Well, for the error part, the effective non-Jovian theory tells us that the transport peak should be of a Breed-Wegener distribution. And then from this distribution, the heavy-quark diffusion coefficient can be obtained by taking its slope at vanishing frequency. So we put up these 2 terms together, and we get the full spectral function and also the corresponding full correlators. But as a first step, we didn't really fit the full spectral function to the full correlators. Instead, we want to look at the UV part first. So we take the difference of the neighboring correlators, which is believed to effectively remove the error contribution. And then we fit this model spectral function to these different correlators. We see that with tiny modifications to A and B, you see here A is close to unity and B is close to 0 for both charmonia and bottomonia, that our model spectral function could describe our data very well. You see here, these colorful bands, which are the model correlators, agree well with the colorful dots, which are our lattice data. And it's the same for charmonia and the bottomonia. And we explain the minor modifications in A as the uncertainties in perturbative normalization. And for B, it's the uncertainties in the determination of pole mass. Now I show the UV parts of the spectral functions of psi and upsilon obtained from our previous slide. So these dashed curves here are the original perturbative calculations. And the solid curves here are our field results. We could see that the modifications are very small. And we also cross-check our results with a maximum entropy method, where we use the previous field results as the default models. And we found that the outputs are exactly the same as the input default models. So we are confident to conclude that for charmonium, we don't need a random peak to describe our data, even at 1.1 TC. While for bottomonium, the random peak could survive up to 1.5 TC. Now we come to the transport contribution. So to see how large it is, we can compare the model correlators to the full lattice correlators. And the difference gives how large the transport contribution is. You see here, actually there are some deviation in these two correlators. And the deviation for the charmonia is larger than that in the bottomonia, which means we have more transport contribution for charmonia. But we want to have a close look at this transport contribution. So we have to make use of this Breit-Wigner ansatz for the transport peak. Now we try to fit the full spectral function to the full correlators. Then we will have 4 fit parameters: the quark mass m, the width eta, a, and b. But we could use Einstein relation so the fit parameters become the heavy-quark diffusion coefficient d, eta, a, and b. But unfortunately, that we found that if we want to fit 4 parameters at the same time, we cannot get any stable results. Since this way doesn't work out, so we tried another way. We try to solve this transport peak directly from this equation. First, we calculated the transport contribution from previous slide by subtracting the model correlators from the full correlators. And for the right-hand side, we just inserted this transport peak to here. And now we have 2 free parameters, eta and d. So we have 2 options. We either fix eta solve d or fix d solve eta. And our choice is to fix 2 pi td to some numbers that are kind of reasonable according to some other lattice studies. And we found that even we have different values for 2 pi td, they all could describe our data equally well. And we can only have a very tiny curvature in our transport contribution. This indicates that currently it might be very difficult to resolve D from our mesonic correlators. So we turn to some simpler situation. We consider the heavy-quark mass limit in the following. Following this strategy, we could first construct kinetic mass dependent momentum diffusion coefficient kappa m. And through Einstein relation, it's related to the heavy-quark diffusion coefficient D in this way. To get rid of this mass dependency, we could send it to infinite in non-driven theory. And when we carry out this large quark mass limit, we found that the false correlators appearing in the definition of kappa will reduce to color electric correlators. And to calculate on the lattice, we perform analytic continuation, and we arrive at this equation for the color electric correlators. And we discretize it following this diagram. And we will see that the kappa could be obtained from the spectral function encoded in this correlator. The benefits of using these color electric correlators include first, it's cheaper to calculate on the lattice than the mesonic correlators. And the second is the spectral function encoded in the correlators has less structures, so it will be easier to extract. Actually, the color electric correlators have been intensively studied on the lattice using different noise reduction technique, like multi-level and integration. However, these techniques are only applicable for pure gauge fields. If we want to include the dynamic quarks in full QCD, then only gradient flow method could be used. The gradient flow is nothing but a diffusion of the fields along extra dimension, which we call flow time t. And then any operators at finite momentum could be expanded as the renormalized operators at 0 flow time with some coefficients. There are many applications for this method, and in this work, we use it as a noise reduction technique. Okay, this is the lattice setup for the calculations of the color electric correlators. So we have, again, 5 different large quenched tropic lattices. So on each lattices, we tune the bit value, so they are all at the same temperature, 1.5 TC. And we generate 10,000 configurations in each case, and we flow the gauge fields to many intensive discrete flow times, which allows us to perform reliable continuum extrapolation, also the 0 flow time extrapolation. These two extrapolations are required by this gradient flow method to reach physical quantities. But I have to say that in this gradient flow method, you cannot flow the gauge fields too much, otherwise it will destroy all the signals. So we have to figure out how much we could flow. Our collaborators have calculated these correlators perturbatively in both a continuum case and also on the lattice. So this plot shows you the correlators, the flowed correlators at the different flow times. And we could see that as we flow more and more, then more and more correlators, at smaller distances will be destroyed, where the correlators at large distances remain not affected. Actually, if we allow the flowed correlators to deviate from the unflowed correlators by at most 1%, then it will define a perturbative flow time limit. Now we put these flow time limits on our lattice data. They are the colorful dots here. We could say that the correlators beyond the flow time limit will drop quickly, which means the signals are destroyed. While for the correlators within the flow time limits, you will see that the error size is decreasing as you flow. So this verifies that we could use it as a noise reduction technique. Now we consider how to send our lattice correlators to the continuum limit. So these two plots shows you the correlators on different lattices at different flow time. Here, this dashed vertical line is the perturbative flow time limit, and only the correlators right of it could be used in the continuum extrapolation. We could see that as we have a larger flow time, then less and less data points could be used. However, the flow is also removing the lattice effects. As you see, the disordering appearing on the left-hand side is gone on the right-hand side. And then we use this ansatz to carry out the continuum extrapolation. And we see that this ansatz does work very well for our data. Now we repeat this procedure for different flow times. And now we got these continuum extrapolated data points at a different flow time. We could see that for each tau t, that is the different colorful curves here, a very nice linear behavior in flow time can be seen. So we just perform a linear fit in flow time. And the data extrapolated to 0 flow time here is summarized as the blue curve here on the right-hand side. And this orange curve is from this work using the multi-level algorithm. We could see that these two methods agree well with each other, and only a small overall shift can be seen, which we explain as the difference in the renormalization, as the correlators measured under gradient flow are automatically non-perturbatively renormalized, while for multi-level algorithm, we have to renormalize it perturbatively. Now we try to extract the spectral function from our correlators. So again, for the large frequency part, we have this perturbative calculation, which tells that the spectral function should be linear in frequency cubic. Well, for the small frequency part, it's linear in kappa times the frequency. While in the intermediate range, we need some smoothing functions to connect these two parts. There are several different choices for these smoothing functions, and we will use some of them, which we could as the systematic uncertainties. So on the right-hand side, we show the difference of the fitted correlators and our lattice data from different models. We could see that this difference is very close to 0, which means our model could well describe our lattice data. And we summarize the resultant kappa value on the right-hand side here. And we also compare it with the one obtained from this work using multi-level algorithm. We could see that they are pretty close to each other if you compare these numbers. And recently, there is another lattice calculations for this quantity using, again, multi-level method, and their values are also close to ours. So in this talk, I have shown you that we use perturbative-inspired models to describe our lattice data that has been interpolated to physical gypsum and epsilon mass. And our analysis say that we don't need a randomness peak for charmonia to describe our data even at 1.1 TC. While for bottomonia, the randomness peak could survive up to 1.5 TC. And we also tried to extract kappa from the non-perturbatively renormalized color-electric correlators. And our results are consistent with those obtained from other lattice studies. I have to say that all the results that I show in this talk are obtained in the continuum limit, but in quenched approximation. And our next step would be extending our studies to full QCD using large and fine 2+1 flavor His configurations. And recently there is another study calculating the next leading order correction to the kappa, which can be obtained from color magnetic correlators, which we will consider in our future work. Of course, going from quenched approximation to full QCD the physics would be complicated. A lot of things will be changed. Basically, the physics is becoming more non-perturbative. So the perturbative models that we used in this talk may not be applicable anymore. And also in the full QCD, we have quarks. So we need to consider the flow of quark fields in the gradient flow method. But we don't know how to do it yet, or whether it's necessary at all to flow the gauge fields, the quark fields. Even though we will have more difficulties in full QCD, but it's worth doing it. I mean, we are approaching the reality in full QCD. Thank you.
Thank you very much.